this lesson, we're going to look at sample surveys. One of the central topics in statistics that we concern ourselves with is to stretch the data we have at hand, which is our sample, and apply that to the world at large, the population. If we'd like to know about an entire group of individuals, which again is a population, we need to examine a smaller group of individuals, or a sample, because populations, as we know, are too large, so it's very impractical, if not impossible, to look at an entire population. Polls, which you're probably familiar with, or sample surveys, are designed to ask questions of a small group of people in the hope of learning something about the entire population. How can we ensure that a claim about a sample is representative of the entire population? Of course, we'd want to make sure we include the groups of people that we're interested in. Selecting a sample to represent an entire population is more difficult than it sounds. Sampling methods that by their nature tend to over or underemphasize some characteristics of the population are said to be biased, so we need to be really careful of bias. Conclusions based on samples drawn with biased methods are inherently flawed, so any information we obtain from those samples is useless. So how do modern polls or surveys get their samples to represent the entire population? They select individuals to sample at random. Okay, that is the key. Randomizing protects us from the influences of all the features of our population by making sure that, on average, the sample looks like the rest of the population, so it's representative. Not only does randomization protect you against the factors that you know are in the data, it can also help protect against factors you didn't even know were there. Here's the summary statistics comparing two samples of 8,000 drawn at random from a company's database of 3.5 million customers. So we have sample 1 and sample 2. We're looking at the mean average age, the percent that are female, the mean number of children, mean bracket, mean wealth bracket, and then whether they are a homeowner. Do you think these samples are representative of the population of the company's customers? So in this case, I would say that the samples are very similar to each other with respect to the 7 variables. If you take a look at the data, they're not very far off from each other. So randomizing has already matched them pretty closely. And since those two samples don't differ much, I would assume that they don't differ from the rest of the population. So the key takeaway here is they're very similar. That's the symbol for similar, by the way. So we have similar samples, which equates to similar populations. So whatever conclusions we draw from the two samples we have, we can probably apply that to the populations from which they were drawn. How large a sample do we need for the sample to be reasonably representative of the population? So this might surprise everyone. What matters is the number of individuals in the sample, not the percentage or the fraction. So for example, a random sample of 100 students at Valencia College represents the student body just about as well as a random sample of 100 voters represents the entire electorate of the United States. Pretty interesting, right? You would think you would need a certain percentage, but you don't. In other words, the fraction of the population that you've sampled doesn't matter. It's the sample size that matters, or the number of individuals in the sample. Generally, larger and more representative samples are better though. Okay. So another type of sample that we can take, and you may be familiar with this, is called a census. And I know in the United States, the census is performed every 10 years. It's a special sample that includes an entire population. Although a census would appear to provide the best possible information about the population, there are a number of ways or reasons why it would not. You can probably think about why that would be. It can be difficult to complete a census. Some individuals in the population can be difficult to locate, so they may not receive their census, or it could just be impractical. Populations rarely stand still, right? People move, people die, people are born. And a census can be more complex than sampling. For example, a census records too many college students. They're counted once by their families and another time via the university records. Models use mathematics to represent reality. Parameters are key numbers in those models. A parameter used in a model for a population is sometimes called a population parameter. So just remember that they both start with a P, so it's easy to remember. Okay, we use summaries of the data to estimate the population parameters. So again, we're trying to take a sample, and that sample should be representative of the population. When we draw a good sample that's representative, we can find information about the population that we can apply. So we use summaries of the data to estimate those population parameters. Recall that any summary found from the data is called a statistic. So that's easy to remember because they both start with an S, right? So population and parameter start with a P, those go together, and summary starts with an S, and statistic starts with an S, and those go together. Sometimes you'll see the term sample statistic. You're already familiar with two parameters, the mean, right, mu, and the standard deviation, sigma. Both Greek letters. We always use Greek letters for parameters. If you'll remember in chapter 6, we talked about correlation and we used the letter R for that, right? Now, you may wonder why, and that's because the corresponding correlation in a model for the population, so population again is a parameter, we use Greek symbols, it's actually the Greek symbol rho, which looks like a P, okay, but it's rho, R-H-O. In chapter 7, do you remember what B1 represents? It was the slope of the linear regression estimated from the data. But when we think about a linear model for the population, we denote the slope parameter beta 1. So that's the Greek symbol beta. Population model parameters are not just unknown, usually they are unknowable. Again, for various reasons, one of them being populations are too large and they're also, changing. So we have to settle for sample statistics. Those sample statistics, like if I take a good sample and I find an average of that sample, that should tell me, okay, here's my population, and it should represent the population parameter, in this case, the average. What about proportion? Suppose we want to talk about the proportion of teens who don't wear seatbelts, for example. Okay, what we're going to use for the population parameter is P. You would think we would use the Greek letter pi, right? But we know that pi actually is already used. It's 3.14. So we use P instead, and the P hat is our sample proportion for the data. So in other words, we know that the population of teens here that don't wear seatbelts is P. But the way we obtain that is by taking samples from our population, and all those samples would be P hat. So if I take a sample, the proportion of teens who don't wear a seatbelt might be different than the proportion of teens in this sample who don't wear a seatbelt. But all of these samples lead us to what the true population proportion of teens who don't wear seatbelts is. Here's a quick little summary of the statistics. So we've got our summary statistics and our population parameters here. Recall that we want the statistics we compute from a sample. As we've been saying, we want it to reflect the corresponding parameters accurately. A sample that does this is said to be representative. So we've been using that term a lot so far in the lecture. A biased sampling methodology tends to over or underestimate the parameter of interest, and we don't want that. Please pause the video and read the next 5 problems, and you can unpause it when you're ready to review your answers. Various claims are often made for surveys. Why is each of the following claims not correct? Letter A, it is always better to take a census than to draw a sample. So for this one, it can be hard to reach all the members of a population. It can take long, so the circumstances can change. So we know that that's false, right? Letter B, stopping students on their way out of the cafeteria is a good way to sample if we want to know about the quality of the food there. Again, a false statement. Students, the sample's probably biased because students who didn't like the food at the cafeteria might choose not to eat there, so you'll never get their opinion or their response. Letter C, we drew a sample of 100 from the 3,000 students in a school, and to get the same level of precision for a town of 30,000 residents, we'll need a sample of 1,000. Again, that's false. If you'll recall that it's not the percentage or fraction of the population, but rather the number of participants or people in the sample. So it's the sample size that matters, not the fraction of the overall population. Letter D, a poll taken at a statistics support website garnered 12,357 responses. The majority said that they enjoy doing statistics homework. With a sample size that large, we can be pretty sure that most statistics students feel this way too. So this website might be, more hit on by students who are enthusiastic about statistics, right, than the overall population of stat students. A large sample cannot compensate for bias. So even though they have a ton of responses there, the people going to this website could be people who are enthusiastic about statistics. So they're going to, of course, go to the statistics support website. Okay, so you can't say that students, most statistics students feel that way. In letter E, the true percentage of all statistics students who enjoy their homework is called a population statistic. And again, it's not statistics, it's population parameter. Okay, we would have summary statistics. That would be if we took samples of students who enjoy doing their homework, and those samples should give us the population parameter, the true percentage of students who enjoy doing their statistics homework. We're going to stop the video right there. In the next video, we're going to look at different sampling techniques. How do we get a good sample? Have a good day, everyone.